this video, we'll talk through the Advanced Higher Chemistry Unit 1 topic of shapes of molecules. At the end of this video, you should be able to compare the strengths of electron pair repulsions, be able to determine the number of electron pairs surrounding a central atom, be able to state the arrangement of electron pairs around a central atom, be able to state the shape of molecules and polyatomic ions using VSEPR theory. When it comes to looking at the shapes of molecules, we need to consider the number of electron pairs. This depends on how many electron pairs are surrounding the central atom. Not all pairs of electrons will be involved in bonding. Ones that are not involved in bonding are known as lone pairs of electrons. If we look at two examples of methane and ammonia, methane has 4 pairs of electrons, all of which are bonding electrons. Whereas in ammonia, there are still 4 pairs, but only 3 of them are bonding, and we have 1 lone pair of electrons. Electron pairs are negatively charged and will repel one another. There are different strengths of repulsion depending on if you have non-bonding pairs or bonding pairs. The strongest repulsions will be between non-bonding and non-bonding pairs of electrons, followed by non-bonding to bonding electrons, and then bonding pairs to bonding pairs will be the weakest repulsions. The arrangement that these electron pairs take up will minimise the repulsion and keep the electron pairs as far away as possible from one another. This gives us 5 main shapes that the electron pairs will occupy. We have our linear. If there's 3, it will be trigonal planar. 4 gives us tetrahedral. 5 trigonal bipyramidal. And 6 will give us octahedral. We need to be able to calculate how many electron pairs are in a molecule or polyatomic ion. In order to do this, we need to take the number of valence electrons on the central atom, add on the number of bonded atoms, and then divide that by 2. Back to methane. Methane has a central carbon atom. Carbon has 4 valence electrons. We have 4 hydrogens attached to the carbon, making a total of 8 electrons, which is 4 pairs of electrons. Because we've got 4 pairs of electrons, these will take up a tetrahedral shape around the carbon. When we're dealing with ions, which you'll often be asked to do at Advanced Higher Chemistry, you need to add on an electron for every negative charge and remove an electron for every positive charge before we divide it by 2 to work out the number of electron pairs. If we have something like hexafluorophosphate, PF6, it has a negative charge on the ion. Phosphorus has 5 electrons. There are 6 hydrogens attached. That gives us 11 electrons, but we need to add on 1 more for that negative charge, giving us 12 electrons. 12 electrons is 6 pairs of electrons. What this means is that we will then have an octahedral shape around the phosphorus. If there are any double bonds in a molecule, we just treat them the same as single bonds. This is because although there are extra electrons present, that extra density will cancel out the extra repulsion from the lone pair. Next thing we'll be asked to do is to use VSEPR theory to work out what the shape of the molecules will be. VSEPR stands for valence shell electron pair repulsion. For this to work, we need to calculate the number of electron pairs, but also then look at how many of those electron pairs are involved in bonds and how many of them are lone pairs of electrons. Going back to our methane, methane has 4 electron pairs, all of which are bonding pairs of electrons. Therefore, the hydrogen atoms around the carbon will take up the tetrahedral shape. In something like water, where we have oxygen, which has 6 valence electrons, and we have 2 hydrogens attached, giving us 8 electrons, or 4 electron pairs. Those electron pairs will have a tetrahedral arrangement around the oxygen. Because 2 of them are non-bonding and 2 of them are bonding, this distorts the shape, and this is why water has an angular shape. What VSEPR theory shows us is that if you have molecules or polyatomic ions which have the same number of electron pairs, they may have different shapes because the lone pairs will repel the bonding pairs and cause a change in shape. You should be aware of the angles of the most common ones, like linear, tetrahedral, trigonal planar. When you have a lone pair involved, those angles will be smaller than expected because of that repulsion we've discussed a few times. Typical exam style question will be asking you that which of the following molecules has the greatest number of non-bonding electron pairs. In both A and D, there are 2 lone pairs on our oxygens. B has 3 lone pairs on their chlorine, and nitrogen has 1 lone pair, and this means that B will be our correct answer. In this question, we're asked about a hydronium ion. These are our various different options. We have our oxygen in the centre, which has 6 valence electrons, plus our 3 from our hydrogens, minus the 1 because it's a positive charge. That gives us 8 electrons or 4 pairs. We have 3 things attached, meaning there's 3 bonding pairs. We have 3 bonding pairs, 1 non-bonding. This will result in a trigonal pyramidal shape, which will give us 3 bonding pairs and 1 non-bonding pair. Our next question asks us which of the following does not have a trigonal pyramidal shape. This next question asks us which of the following does not have a trigonal pyramidal structure. We're going to go through the VSEPR theory for each of them. Boron has 3 valence electrons plus the 3 things attached, gives us 6 electrons or 3 pairs. Nitrogen has 5 valence electrons plus the 3 hydrogens attached, gives you 8 electrons or 4 pairs. Oxygen has 6 valence electrons, plus the 3 from the hydrogen, minus 1 because it's a positive charge, gives you 8 electrons or 4 pairs. Phosphorus has 5 valence electrons, 3 things attached, giving us 8 electrons or 4 pairs. We can then talk about, well, the first one has just 3 bonding pairs. The B, C and D all have 4 pairs of electrons, 3 bonding, 1 non-bonding. All 3 of them will take up the same shape. That shape it will take up is the trigonal pyramidal, meaning that our answer is A, which would have a trigonal planar structure. This is one of the cases where, because the other 3 answers are all the same, they all had 3 bonding pairs and 1 lone pair, we're looking in this case for the odd one out, which would give us A as our answer. In this question, we're given a diagram of a square planar structure where the wedges represent bonding pairs of electrons and the dots are representing non-bonding or lone pairs. We're asked which of the following chemicals would have a square planar structure. This means we're looking for one that has 6 pairs of electrons in total, 4 of which are bonding, 2 of which are non-bonding or lone pairs. We're going to go through the same process as before, look at the central atoms, add on how many chemicals are attached. If it's a positive charge, take away an electron. If it's a negative charge, add on an electron. What we'll see here is that we end up with, so for example, in the first chemical, we have 6 valence electrons, 4 things attached, giving us 10 electrons or 5 pairs. We have 4 bonding pairs and 1 non-bonding pair. B has 8 electrons, which is 4 bonding pairs. C, xenon has 8 valence electrons plus the 4 fluorines, giving you 12 electrons in total, 6 pairs of electrons. Aluminium has 3 valence electrons, 4 hydrogens attached, plus 1 more for the negative charge, giving you 8 electrons, 4 bonding pairs. What we can see then is that the one that has 4 bonding pairs and 2 lone pairs is C, so xenon tetrafluoride would be our correct answer. In this last type of question, we're asked about a particular bond angle. We're going to follow through our VSEPR theory again. We're going to get to the shapes of the molecules. We've got octahedral, tetrahedral, tetrahedral, and tetrahedral. Once we become familiar with their different shapes, we can see that tetrahedral has an bond angle of 109 degrees compared to octahedral, which has 90-degree angles within it. Another way we can do this is by looking at the odd one out. We have 3 tetrahedrals which would have the same bond angle versus A, which is an octahedral shape. Hopefully by the end of this video you are now able to compare the strength of electron pair repulsions, be able to determine the number of electron pairs surrounding a central atom, be able to state the arrangement of electron pairs around the central atom, and be able to state the shape of molecules and polyatomic ions using VSEPR theory. Thank you for watching, goodbye.